All right. So after I made these attack projects where you poison either the training data or the data that's being classified later, I wondered if there was a defense, and there is a defense. This was developed by some researchers. I must say it took me a whole week to write this project because they made it really complicated. And one thing that really bothered me is they didn't have any proof that the defense was effective. And I wanted a nice, simple way to see if it was working. So I got that finally working, and I'm pleased with this. It's not hard to do. It took me a long time to figure it out. But this thing is called deep neural rejection. And this reminds me of a question that came up in my last class in Chicago. Someone said, so unlike we've seen how Google cannot figure out how to make their LLM stop saying bad things. So they just block one category of question, like it won't tell you who won the election in 2020. But Microsoft does much better with GitHub. And she said, how do they do that? And I said, well, they use a large language model. What else could you use? They use an AI to fix the problems with the other AI. That's pretty much all you can do. And that's what this is going to do. So deep neural rejection. Remember how the last project I showed you, you took some of the images and poisoned them by putting some little speckles of white on them, which would confuse the model and cause it to learn badly. So how hard would it be to detect poisoned images? And it turns out not to be too hard. What you do is you feed it into some LLMs that come up with a number which measures some quality of the image. And you can't say, it'd be nice to think this is something like the standard deviation of the X coordinate or the intensity or something, but these are things that it's going to learn. It's going to extract some measures, which it will adjust and learn from. And then it's going to plot the probability of that. And then it's going to find ones that are outliers. So things that are exceptional. Remember, we talked about this before in the first bit on the production line. You have a group of things that are all pretty much the same, and you have some that are outliers. Those are the products that are defective. So it's going to find the ones that are defective along these classifying things. So you download some data and you look at the images, and it's the same old stuff we've seen. It's handwritten digits, and we know what they should be. And so the question is, the unprotected model, when you do predictions, we can see, and it is not perfect. You can see it makes some mistakes. So image number eight, for example, here's the output of the model, and the highest positive number is the result. And here's the digit. So here's an 8, and the probability of it being 8 is only 488. It has 1186 of being a 6. So this is a misidentified model. It really is more likely to be a 6 than an 8 in the interpretation of the model. Now, this one, 4, this works much better. Here's your 4 is positive 5,000, and all the other scores are pretty much negative. That's a good one. It's not 4 it could read. It couldn't really read that 8 very well. All right, so that's the original model. So now we're going to attack the unprotected model. So we create evasion images, images that are going to fool it, and then have it try to predict them. And the end result is when I give it evasive images, it gets them all wrong. It thinks this is an 8. It thinks that is an 8. It thinks that is a 9. All 20 of them are wrong. That's the unprotected model. The poisoning is very effective, or the evasion in this case. All right. And so all 20 attempts to evade classification succeeded. So now we add the deep neural rejection. You add the rest that will now measure some parameter of the numbers and throw away the ones that are outliers by 1%. And after you do that, then you'll see, is this the one? Yeah, there's an R. Now, see, here's the prediction and the right answer, but for some of them, the prediction is now R, which means it rejected this image. It noticed this image was an outlier. So several of the images, it did reject them. And so now you can prepare attack images. And when you do that, here's the attack images like ones you've seen before with the snow in them. But when you perform the attack, only 6 of those 20 attack images got through. The rest were detected as suspicious looking images, and it wouldn't use them. And so the end result is it's less effective. The poisoning is less effective. So that's the point. You can see it works, and it's actually not very hard to understand. Now that you know that some clown is sneaking in malicious images, you just find the outliers before you go. So, all right. And there's various modified versions of this to play with, but I was glad to get a defense to go with the attacks. Stop this one.